All right, welcome back to the Neutral Axis. My name is Wilson Raposo Olinik, and I'm a structural engineer based in Southern California. My goal with the Neutral Axis is to be a resource for engineers through tutorials, design examples, personal and professional development content, and interviews of the future faces of engineering. If any of this appeals to you, I would really love if you join the Neutral Axis by subscribing to this channel. It would really go a long way in helping this channel grow, and that way you'll never miss any content. All right, let's talk some concrete. Reinforced concrete beams are structural elements that are designed to resist loads transversely, and you'll find them in different types of structures such as concrete beams, concrete parking garages, and bridges. And typically they support other structural elements such as concrete walls, concrete slabs, concrete columns, and pretty much any other structural element made of any other material. Generally speaking, these can be simply supported beams, continuous over the support, or cantilever. However, the design of reinforced concrete beams is very similar regardless of the application. Today, I will go how to determine the positive flexural capacity of a singly reinforced concrete beam in 5 simple steps. As you can see on the screen, we have a problem statement that requires us to determine the nominal positive flexural capacity of a singly reinforced rectangular concrete beam. In this case, the beam is a 12-inch wide by 20 inches deep concrete beam with number 4 stirrup side 9 inches on center and 4 number 8 flexural longitudinal bars. As I'm solving the problem, I will be writing information that we already have. That way we can trace the information that 1, we have, 2, we need to find in order to get the final answer. So I will create a single section in here where I'm going to list down the information that we have. And the first information that I see clear in the problem statement is that the clear cover of the section, which we will call C, is 1.5 inches. That means that the distance from the bottom of the section to the shear reinforcement in this case is 1.5 inches. It's a clear distance, it's a clear cover. We also know that the longitudinal flexural bars are 4 number 8 bars. So that means that the total area of steel is 4 times the area of a single bar, which for a number 8 bar, that would be 0.79 square inches. We also know that the compressive strength of the concrete F prime C is 4,000 psi. And for the sake of obtaining smaller numbers, I'm going to convert that immediately to KSI. So 4,000 psi is the same as 4 KSI. And then we know that the yield stress of the flexural and shear reinforcement is 60 KSI. So I'm going to write down that information right there. And with that, we know that our depth, or I'm going to call this DT, is, and then that the width of the section, which I'm going to call B, is 12 inches section. So the effective depth of the section would be the distance from the top of the section all the way down to the center of the flexural reinforcement, which in this case we're going to call D, and we can calculate D as the total depth of the section, which is this number that we have in here, minus the clear cover, which is clear from the bottom of the section to the shear reinforcement, minus the diameter of the stirrup, which we will call DS, minus half of the diameter of the flexural reinforcement. And the reason why we're using half of it is because we're going to the centroid. So going from the bottom of the section, that means that we're only taking up to the center of the bar. So half of the diameter. Doing the quick math for this, that means that DT, which is 20 inches, minus the cover, which is 1.5 inches, minus the stirrup diameter, which is the number of the stirrup divided by 8 inches. So it will be 4 divided by 8 inches, minus half of the diameter of the flexural reinforcement, which in this case will be a number 8 bar divided by 8 is 1 inch. So I'm going to write down that's 1 inch divided by 2. And all of that equals to 17.5 inches. So we have an effective depth of 17.5 inches. The first step in determining the nominal flexure capacity of the concrete beam is to set up a strain and stress compatibility. One of the design assumptions that you make in concrete design is that you have strain compatibility, and the strain varies linearly from the top of the section all the way to the bottom. To determine the nominal moment capacity of the section, we have to set up the strain diagram with the concrete failing and crushing. So we know that per ACI 31814, this value, ECU, is 0.003. So we can start the diagram in the section with this value being 0.003 right? And let's draw this straight line over here to represent the axis. And like I said in the previous step, the strain varies linearly from the top of the section all the way down to the flexure reinforcement. So if we start with 0.03 at the top in compression, at the compression extreme fiber, we go down to the depth of the flexure reinforcement, and we have a value that is equals to ES, or the strain in the steel. We already know that the depth to the steel or flexure reinforcement is D, and the location where the strain is 0 is called the neutral axis, just like the name of this channel. And we're gonna draw this line over here that passes through it, and we're gonna go over why this location is important. The depth to the neutral axis is from the top, the extreme concrete fiber, compression fiber, is called C, and we already have that listed down here in the diagram. And something that we can look at is the strain in the flexural reinforcement. The strain in the flexural reinforcement, ES, is unknown at this point. However, we can go with the assumption that the tensile reinforcement in the section has yielded. And it's an assumption that goes in hand with the requirement of ACI 318 that all beams must be under reinforced. When a beam section is under reinforced, it ensures a ductile failure in the section by the steel yielding before the concrete crushes. And the reason why this is an important requirement is because we want to make sure that the section behaves and fails in a ductile manner instead of having a brittle failure, which would occur if the concrete crushes before the steel has yielded. We can go ahead and denote that the steel has yielded, which translates to the strain in the steel being greater than the yield strain of the section. And this yield strain of the section is simply, by our knowledge of strength of materials, the yield stress of the section divided by the modulus of elasticity, which will be 60 KSI divided by the modulus of elasticity of steel, which is 29,000 KSI. And this translates to 0.00207. So we're going with the assumption that the strain in the steel is greater than 0.00207, and it's an assumption that we must later confirm that the assumption that we made that the steel has yielded is still true. Now that we have completed the strain diagram in the section, we can go ahead and look at the stress distribution in the section. The neutral axis is still at the same location, right? Because strain and stress are linearly proportional up to the yield point, up to the proportional limit. And in this case, for the tensile stress side, which is below the neutral axis, in this case, one key assumption that is made in concrete design is that any concrete below the neutral axis in the tensile stress area is ignored. And it's because concrete is known to not be good in tension. It's usually only good for compression. And the assumption that is made is that the steel is completely resisting all of this tensile stress in the section. So we can go ahead and draw a vertical line over here to start building our stress diagram. And the stress in here will look something like, the steel reinforcement is still there. And we're going to denote this stress block in the steel, which looks something like this. And then this will be denoted by Fs, which is the stress in the flexural reinforcement. So that's all about for the tensile stress, which is completely resisted by the tensile reinforcement. In the compression side, which is above the neutral axis in this case, an effective stress block is assumed with an average stress of 85% of the F prime C, the compression strength of the concrete. But we don't know what this depth of the stress block is. It's usually denoted by the letter A, and this variable A is related to C, which is the depth to the neutral axis, by a factor that we call beta 1. So A equals beta 1 times C. And per ACI 318, beta 1 is equals to 0.85 for all F prime C up to 4,000 PSI inclusive. Since our F prime C in this case is 4,000 PSI, that means beta 1 in this case is 0.85. Now that we have built the stress distribution, we can go ahead and look at the equilibrium in this section. In this case, the steel reinforcement obviously has a tension force, which is acting at the center of this tensile stress. And the tension force would just be equal to the stress in the flexural reinforcement times the area of steel. Since we already assumed that the steel has yielded, that means that Fs is automatically equal to Fy, which is the yield stress of the steel. So Fs in this case is equals to Fy, which is 60 KSI, and As is 3.16 square inches as we calculated towards the beginning of the problem. So the tension force is equivalent to 60 KSI times 3.16 square inches, and that is equals to approximately 190 kips. So we can go ahead and write 190 kips for the tension force. Now let's look at the compression force. Now that we have determined the tension force resulting from tensile stresses, the next step is to determine the depth of the compression stress block. We already know that the compression stress block has a depth of A, which is related to the depth to the neutral axis by beta 1. And this stress block will look something like this, with a depth of A and a width of B. And we already know that the stress is 85% of F prime C. So if we were to calculate the resultant in the compression stress block, that would tell us that the compression force, or big C, let's not confuse this with the depth to the neutral axis, which is little c, big C would be equal to 0.85 F prime C times A times B. We already know that B is 12 inches. We already know that F prime C is 4,000 PSI, but we don't know what A is. So that means that we have to solve A. This is the point where we set up equilibrium in the section. The resultant in the compression stress block will act as the centroid of the stress block. So if we denote this by letter C, big C in there, we can clearly see by the arrows that because there's no axial force in the section, that means that the tension force from the tensile reinforcement must be equal to the compression force from the compression stress block. So that means the C is equals to T, right? So knowing that T is 190 kips, we can solve for A, and A is equals to T divided by 0.85 F prime C times B. And plugging in those numbers, we get that A is equals to 4.66 inches. So we can write this down in here, 4.66 inches. And now that we have determined A, we can determine what the depth to the neutral axis is for little c. A is related to little c by beta 1. So that means that solving for C, C is equals to A divided by beta 1, or 4.66 inches divided by 0.85, which is 5.48 inches. So that means that the neutral axis is located at a distance of 5.48 inches from the top of the section. And we can write that down here. Let's just make this a little bit clearer. C is equal to 5.48 inches. Now that we have determined the depth to the neutral axis, the next step is to confirm that the flexure steel has indeed yielded. And to do this, let's look at the strain diagram that we built on step number 2. We already know that the strain in the concrete ECU, let's denote that over here, is 0.003, but we don't know what this value is, which is the strain in the steel. And we can determine that by using the law of similar triangles. The law of similar triangles tells us that two similar triangles, the properties of two similar triangles are equivalent. So in this case, we can relate the depth to width ratio of the triangle above the neutral axis to the depth to width ratio of the triangle below the neutral axis. That means that the depth of the triangle above the neutral axis, which is letter C, divided by its width, which is ECU, is equal to the depth of the triangle below the neutral axis divided by its width. We don't know what this depth is because this is the depth of the section, right? But we know that the total depth of the section to the flexure reinforcement is D, and we know that up to this point, the depth from the top of the section to the neutral axis is C. So that means that this value here must be D minus C. Therefore, we have the C divided by ECU is equal to D minus C divided by the width of the triangle below the neutral axis, which is ES, or the strain in the steel. We already know what D is, we already know what C is, we already know what ECU is, and we already know what C is. So we can do a cross multiplication in here, and therefore C times ES is equals to ECU times D minus C. Solving for ES, we get that ECU times D minus C divided by C is equals to the strain in the steel. If I go ahead and plug in those numbers, That means that ES is equals to 0.003 times 17.5, which is the effective depth that we determined at the beginning of the problem. Solution minus C, which is 5.48 as we determined in the previous step, divided by 5.48 inches. And that means that the strain in the steel is equal to 0.00658. Looking at the strain value, we can confirm that the strain in the steel, as we determined, is greater than EY, which is 0.00207, as we determined in the previous step. So that means that the strain in the steel is indeed greater than the yield strain, which means that steel has yielded, which means that our assumption at the beginning of the problem statement is confirmed. Now that we have confirmed that the flexural steel reinforcement has yielded, we can go ahead and go to the fourth step of the problem. In this case, the fourth step is to actually determine the nominal moment capacity in the section. The nominal moment capacity in the section is simply the couple that is formed by the net resulting compression force and the tension force in the section. In step number 2, we already determined the couple. We determined the compression force and we determined the tension force in the section. We already know that C is acting at the centroid of the stress block. That means that from the top of the section, C is at a distance of A over 2, or the depth of the stress block divided by 2, because it's acting at the centroid. And we also know that the depth to the flexural reinforcement is a value of D, right? So then we can go ahead and determine the distance in between the two forces, which will create the force couple in the section. So in this case, the nominal moment capacity in the section is either the tension or the compression force. Is usually more common to use the tension force. And remember, T equals C. So it doesn't matter which force we use to describe the force couple in the section. Therefore, the nominal moment capacity is the tension force times the distance in between the two forces, right? So in this case, that will be a value of D, right, minus A over 2, since the compression force is at a distance of A over 2 from the top of the section. And there you go. That's just the nominal moment capacity of the section. And if we plug in those numbers, that means that the nominal moment capacity in the section is 190 kips times 17.5, as we determined at the beginning of the problem, minus A over 2, which is 4.66 inches divided by 2. And all of that is equal to 2,882.3 kip inches. And if we convert that to kip feet, that is equivalent to approximately 240 kip feet. So we have determined what the nominal flexural capacity, the nominal moment capacity in the section. But that's not the final step. We still have to confirm that the area of steel in the section is greater than the minimum area of steel requirement set by ACI 318, which brings us to the fifth and final step, which is to confirm that the area of steel in the section is greater than or equal to the minimum area of steel requirement per ACI 318. The provisions of this requirement is located in ACI 318-14, section 9.6.1.2, and it has two requirements. And it tells us that the minimum area of steel is the greater of A or B, and A is equals to 3 times square root of F prime C divided by Fy times BW times D, and B is equals to 200 PSI divided by Fy times BW times D. And in this case, BW is simply the width of the section, which is, we already denoted as B, which is 12 inches. We know that D is equal to 17.5 inches. And then we can go ahead and plug in those numbers to determine which one ends up being the governing. Plugging in those numbers for A, which is the first value, we get that A is simply 3 times square root of 4,000 PSI. And the key here is to plug in PSI and not KSI, because you are using a square root value there. And it's an empirical formula that is based on PSI, times 12 inches times 17.5 inches divided by 60,000 PSI. And that is equal to 0.66 or 0.664 square inches. So now let's look at the value for B, which is 200 psi divided by 60,000 psi times 12 inches times 17.5 inches. And that is equivalent to 0.7 square inches. So clearly the governing value for the area minimum steel is B, which is equals to 0.7 square inches. From the first step, we determined that the area of steel in the section is 3.16 square inches, which means that the minimum area of steel requirement has been met because AS, which is the area of steel in the section, is greater than 0.7 square inches. This brings us to the end of this problem solution. If you found value in this video, please make sure to subscribe and hit the like button. It will go really a long way in helping this channel grow. Let me know what type of videos you would like to watch, any design example that you would like me to go over in the next video, or simply leave a comment with words of encouragement letting me know the things that I can improve, the things that I can work on for the next video, and obviously any topics that you would like me to address in the future. If you would like to see this calculation in PDF format, I have left a link in the description below to theneutralaxis.com, where I will be posting articles and resources to help you thrive in your engineering career. I would appreciate it if you leave a comment in the comment section below. Let me know about you. Are you a student? Are you a college graduate? Are you a professional engineer? Or are you genuinely curious about engineering? Please let me know what type of content you would like to watch, any questions that you may have about engineering in general or structural engineering. That way I can collect this information and consider it for a future video in this channel. Lastly, make sure that you follow us on Instagram at the Nutralaxis blog, and go to our website, visit our website, theneutralaxis.com, to make sure that you stay up to date with the content that is shared in all platforms. Thank you for watching. Thank you for all the support. Again, this is Wilson Repulse Olenek at the Nutralaxis. Until the next time.